So usually when dealing with motion, it's quite useful for us to produce some graphs. And the most common graphs in the IB exams are the distance time graphs and velocity time graphs. And we can get some very important and actually quite easily we can get information from those. So for example here in this distance time graph, okay, we could describe this motion, right? You should all be able to. So if we try to interpret what's happening here, well, first our object starts at rest at the origin, right? Not at rest because it's moving, so we see that distance is increasing with time. So it starts with a constant speed. Distance is changing, right, with a constant rate. Now, when it gets to this point, which is approximately 600 seconds or so, then it stops, and it's going to be stopped. See, there's no distance traveled, no more distance, so it stops, and then it continues. And we can even, for example, compare the speeds, because if we take the gradient of any of those lines, we should find our average velocity, our average speed. So in this first case, if we close a triangle in this first segment here, this first portion of our motion, so let's split this motion into 4 parts. Oh my god, 4 parts, 3 and 4. So in the first one, this is the first one, our height is approximately 100 and the unit is meters, and the time, elapsed time, would be about 600 seconds. Okay, we could have a graph which is more accurate with more divisions here, so we could try to analyze and get a more accurate result, but so far let's assume that it's about 600 seconds. So our speed would be the gradient, so that's rise over run. So if we do rise over run here, rise is 800 meters and run 600 seconds, and we can observe that the units, they match, meters per second. We can cross some of those things out, so we would have 4.3 meters per second, so 4 over 3 meters per second. Or we could express this number as 1.3333, right? So it's a recurring number, right? And there you go. And the same thing as 1.3 meters per second. So that's our average speed here in this beginning. In this case, we could still apply our gradient formula. The problem here is that if we try to do rise over run, our rise is 0. So time's passing, we are running on the graph, on the x direction, but there's no change in the y direction. So it's 0 over, you could even try to interpret the time here. You could assume, oh, it's about, I don't know, 250 seconds, or I don't know, approximately something like that. But whatever, 0 divided by time will be 0. So our speed is also 0. So in any point when you see a flat line on a distance time graph, your speed will be 0. On this third point, if we simply compare without calculating anything, we could say that, well, this is a larger speed than this first one, right? Because it's steeper. But let's try to calculate the actual average speed. So rise over run again, right? So that's our triangle. Again, let's approximate. Usually we're going to have some better numbers, but let's say that this is almost, if we consider those two, we would have half and half, let's say. Okay, so those, they would add to 100. So let's say 1, 2, 3, 4, about our run would be about 400 seconds, right? Here 3, and then plus 2 pieces. And then what would be our rise? So we are 800 here, and we go up to 3,200. So we would have to do 3,200 minus 800. It's the difference, right? That's exactly what we did here, but mentally. So 3,200 minus 800 would be 2,400 over 400. So we can cross out some of the things. 24 divided by 4, so that's 6. 6 meters per second. We're keeping the units, so that's 3,200 meters, right? That's 800 meters. So everything is up to is in the SI unit. So there you go, 6 meters per second. And we can clearly see that it's larger. It's considerably larger. It's almost 4 times larger. Now let's go to number 4. So 4 here, we have a small triangle again, right? And if we notice, if we make the same approximation that we did before, let's say that this piece and this piece, they are about a whole piece, so that would be 100, and this 100 as well. So our run would be 200. That's the time, and we have gone up by 2 units here, by 2 squares, so by 2 rectangles. So we would go up by 200. So it would be roughly 1 meter per second. And there you go. Now, so far, we have only discussed about our average speed. But there's also what we call the instantaneous speed. And it's actually what we have in our everyday lives. It's the most common kind of speed that we find. When you, for example, when you're driving and you look at the speedometer of your car, well, you don't drive yet, right? But when someone you know is driving or giving you a lift, you can see there is a speedometer. It's basically a device in the front of the car, close to the driver's seat, and the person can analyze what instantaneous speed is she or he driving the car at. That gives you an instantaneous value. So at each second or at each point in time, you can find out what's your instantaneous speed. And how does that work? Well, previously we have considered, for example, a bus or a car starts driving at a constant speed and gets to a certain point where it stops. So that could be the graph of that motion, right? Distance and time. Distance, time. Okay? Now, most of the time that's not true. Our vehicle will change its speed often, and will accelerate, will decelerate. We'll find some traffic lights, or a driver will stop to get a passenger. And well, usually the speed is not constant. It's not like that. So for example, we start the engine of our bus or our car, so it slowly accelerates, right? So its speed increases slowly first, and then it accelerates, and then there is a bus stop, so it stops for a passenger, and then it accelerates again, and then there is a traffic light. It has to stop, and then it accelerates again, and then it stops. So you can see that, in fact, if we take the average values, the average distance from this point up to this point, and we take the total time, the speed will be the same, right? This red line could be the approximation, the average velocity, or sorry, the average speed for this blue motion, right, of this bus. However, if we take any points in that line at any time, We can see that, well, for example, here our our speed would be different than the red one, right? If we get tangent lines at any point on this blue line, we would get our instantaneous speed, right? That's our instantaneous speed. So at any point you can get a tangent, which is the gradient, right? But in a curved line. So we can see that there will be, for example, here at the beginning, if we get a flat line, it would be basically, we get a tangent line, it would be flat. And this flat line, like we saw in the previous example, it means that the speed is 0. Then the speed increases, you can see that it gets steeper, and then it gets less steep again, and then it's flat again. So there we go. The green lines here would represent our instantaneous speeds. If you're into calculus, in fact, your instantaneous speed would be the derivative of time, of position in respect to time, or the rate of change of position with respect to time. If you have a discrete problem, you would approximate this to delta s over delta t. So this would be a change in position and a change in time. For instance, this would be, let's say, final position minus initial position over final time minus initial time. Alright, so let's do an example now. So we've got a graph here. This graph shows the distance run by a boy, how it varies with time since he began to run. So we can clearly see there are two distinct moments. We have a first moment where the boy is running faster, and then later, after 10 seconds, he probably gets tired and runs a bit slower, up to 30 seconds. That's all we have observed. We don't know what happens next. We don't know if he stopped or whatever. Now, calculate the instantaneous speed at 5 seconds and at 20 seconds. So, the whole point here is, if you observe, it's flat. It's a constant speed. So, the instantaneous speed at 0.5 is the gradient of this line, right? Isn't this the tangent line to this? It is. So it's the gradient. So we can close this triangle here, right? And work out what would be the gradient, which is rise over run. So V, let's say I1, V equals, then rise, which is distance, so it's 48 meters in 10 seconds. So that would be 4.8 meters per second. On the second case, it's also constant speed. It's a different constant speed, but we can still see that it's constant. So we can also close a triangle here and here, right? So this is our rise and this is run. So speed would be, now rise, we have gone from to 90 from 48 over how long? So 30 seconds minus 10. I know this is 20, right? That's the base of this triangle, but mathematically that's what we do. If this was a very strange graph, you could just subtract those two. So 90 minus 48, that would be 42 over 20. So that would be 2.1 meters per second. So as we had predicted, it's a slower speed, much smaller. It's more than twice smaller than the original one. Now, letter B. What is the average speed for the whole 30-second run? So now we have to take total time total distance and total time. So total distance over total time. So if we take total distance over total time, total distance was 90 meters and total time 30 seconds. So 90 meters in 30 seconds, that's 3 meters per second. That's the average speed.